Alright, so the way we approach this is we have two two-part compounds in the first equation. This is a partial equation. There are no products listed, so we have to predict the products. There are two things that I can tell from this. Is double replacement because I have two two-part compounds. If a reaction occurs, it's a double replacement reaction, because if there's no reaction, then basically we'll put NR over here when we get done. But we have H in the front of this formula indicating we have an acid. Then there's an OH in the back of the SROH, and that indicates we have a base, a simple acid and base. Okay, so that means that this is probably going to be acid base. Okay, because if I have H in the front, no H in the back, well, we're going to create water. That's one of our driving forces. So I'm going to put HOH over here. Remember, subscripts like this one do not travel. I know. This 2 here does not travel. The only twos that travel are those that are part of a polyatomic ion. This 2 is not part of the hydroxide ion. Okay, so we're just going to put this over here. This is going to be a liquid. We're going to put the front part of this with the back part of this, and there's a bromate ion here. Okay, we need to know the physical state of this, and we need to know what balance it is. But since I already have a driving force here, I can do either one I want to. It doesn't really matter which one I do first. If I did not know there was a water being made here, then I'd want to find out if this is going to be a solid first, because then it tells me whether I have a driving force or not. Driving forces for double replacement reactions are the formation of water, or the formation of a solid, or the formation of a gas. So bromate has a -1 charge. Strontium has a 2+ charge. You can figure that out from where they are on the periodic table and the systems we used for sort of memorizing what the bromate charge is. So we're going to need 2 bromates. And I'm sorry, this is not bromate, this is perbromate. It still has the same charge, however. And then it's going to be aqueous. Okay? So now we're ready to balance the overall equation. So we're going to list out all the atoms we have here. We have hydrogens and bromines, oxygens, and strontiums. And initially I'm going to have 1 hydrogen here and 2 here. So I have 3 hydrogens. I have 1 bromine here. I have 4 oxygens plus 2, or 6 oxygens, and 1 strontium. If you don't do that in your head very well, then you need to make just do the math over here. Be careful with it. Over on the other side, I have 2 hydrogens in the water. I have 2 bromines, because this parentheses here means, and the 2 outside means that I have 2 perbromates. So I have 2 bromines because the perbromate ion has only 1 bromine. So that's 2 bromines. The oxygens I have, 2 times 4 is 8, plus the 1, that's 9 oxygens, and I've got 1 strontium. So I want to try to get everything equal on both sides. I want to save oxygen for last, hydrogen for next to last, so I need to start with the bromine. Since I have 2 bromines over here, I want to get 2 bromines on the left, and the only thing we can do to an equation to increase the number of atoms is use coefficients. Once you balance the formulas, you must leave them alone. Okay, so I can only use coefficients here. Leading terms, somebody said last week. So I'm going to put a 2 here. That's going to change the number of hydrogens, bromines, and the number of oxygens. Hydrogens, bromines, and oxygens. So I now have 2 hydrogens here, 2 hydrogens here, that's 4. I have 2 bromines, and I have 2 times 4, or 8 oxygens, plus the 2 I have here. So I have 10 oxygens at the moment. Okay? Alright. Now the bromines are balanced and the strontiums are balanced. And since the only thing left are the oxygens and hydrogens, I need to balance the hydrogens next, because hydrogens are always balanced next to last. Since I have 4 hydrogens on the left and only 2 on the right, I only need a 2 here. That's going to change the number of hydrogens and the number of oxygens on this side. That's going to give me 4 hydrogens and 10 oxygens. Okay? Everybody got that? Questions? All right. I'm not going to assign individual points to this. You guys know how to assign those points. Okay? I'm just going to count them off. We've been doing this long enough, you should know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32 points. All right? Yes? Well, I haven't yet, have I? We were supposed to classify it, weren't you? Okay, so this was both acid-base. You could call it neutralization and double replacement. And I've been traditionally giving 5 points for each of those, so that adds 10 points to this, meaning we're going to have 42 points for this one. Okay? Alright, now this is going to be, if there's a reaction at all, this is going to be single replacement. That's because I have an element by itself and an element in the compound that it's like. This is a metal. It's like this aluminum because it is also a metal. We need to know whether this is going to be, if it's going to have a driving force, the driving force for single replacement is the nickel has to be higher on the activity series than the aluminum. And since we are using, if I can find my copy of it, well, I can't seem to find my copy of that. Here it is. I did find it. There it is. Yay. Okay, so in this class, you're using standard reduction potentials, and all you're doing is looking for whether aluminum is lower than, nickel is lower than aluminum. If the nickel is lower, the reaction occurs. If nickel is not, it doesn't. Well, there's aluminum there, and nickel's up here. So nickel is not lower. The nickel metal must be lower than the aluminum ion in order for reaction to occur. So this is a real simple answer, just simply no reaction, and that's worth 5 points. Okay? The next one, if there's a reaction at all, it's going to be double replacement. I have a 2-part compound here. This is sodium sulfate. The polyatomic ion sulfate tends to stay together. Over here I've got a polyatomic ion ammonium. That tends to stay together, and so does the chlorine. Of course, the chlorine is just one atom. But we're going to switch the parts. Okay? Double replacement means I'll take the front part of this and put it with the back part of this, and the front part always remains in the front. So we're going to put sodium and chlorine together. I hope you recognize this one by now. This is just table salt. And I hope you recognize already that this is already balanced. 1 sodium, 1 chlorine. We've used it enough you should kind of know that. And if you have water around, this AQ here and here means there is water around. Table salt is going to dissolve, so you shouldn't have to even look this up. You should know this is aqueous. We've used it enough and worked with it enough for you to know. Now, the front part of this then is going to go with the back part of this. So we're going to put NH4 and then SO4. We could balance this formula first, but really what we need to know is whether there's a driving force. That's our sort of the first thing we need to figure out to save us as much time as we possibly can. So we need to know if this is going to be soluble or not. Well, in the solubility rules, the very first rule says, among some other things, ammonium compounds are always soluble. It also says later on that sulfate compounds are mostly soluble, and there are a few exceptions, but ammonium is not one of them. So this is also going to be aqueous, and that means we do not have a driving force here. Therefore, all we need is NR on the back side of this, and this question is also worth 5 points. Okay? All right. The next equation then, we have carbons and hydrogens in this formula, and oxygens here. That means this must be a combustion reaction. Okay? You don't have to figure out whether there's a driving force or not. For combustion reactions, we always assume they will move forward. We do have to figure out what the product's going to be. And for combustion reactions, that's really simple because they're always the same, at least the combustion reactions we're going to be working with in this class. If you have a hydrocarbon fuel, and all of ours will have a hydrocarbon fuel, and you have oxygen, then you can assume that your products are going to be CO2 in gaseous form plus H2O, also in gaseous form. And the reason we show water in gaseous form is because of the heat. Sometimes you'll see people, even textbooks, where they show water being a liquid. I prefer to show it as a gas because initially, at least, it has to be a gas. Now, when you know the physical states here, well, atmospheric oxygen is always going to be a gas. And we said that if this subscript here is less than 5, then we're going to assume this is going to be also a gas. Okay? Our rule for figuring out whether the hydrocarbons are solids, liquids, or gases, we kept it pretty simple. They're not really as simple as that. We're going to make it pretty simple. We said if this is less than 5, then we'll assume it to be a gas. If this number is between 5 and 15, we'll assume it to be a liquid. And if it's greater than 15, we'll assume it to be a solid. Okay? All right, so now that we have all this done, we're ready to balance the equation. We're going to list all of our elements on both sides. CHO, it's always going to be a sneeze. And we're going to make our grid here for the atom inventory and count all the atoms. I have 3 carbons here, 8 hydrogens, and 2 oxygens. And on the right-hand side, your initial count is always going to be 1, 2, 3. I mean, you can count them up if you want to and see, but they always end at 1, 2, 3. Well, to get the carbons to be the same on both sides, I can only use a coefficient in front of the carbon-bearing compound that's here. That's going to change the number of carbons and oxygens. So I need to recount the carbons and oxygens now. So I have 3 carbons. Here I have 6 oxygens plus 1, or 7 oxygens. Okay? Now we're going to try to balance the hydrogens. If I have 8 hydrogens on the left, to get 8 hydrogens on the right, I need a coefficient of 4. This water has 2 hydrogens, so if I want to get 8, I need a coefficient of 4, because 4 times 2 is 8. That's going to change the number of hydrogens and change the number of oxygens, and so we're going to recount everything now. So I have 8 hydrogens, and the number of oxygens I have is 3 times 2 here, or 6. 4 times 1 here is 4, so that's 10 oxygens I have. Well, that makes balancing the oxygens on the other side pretty easy. All I need is a 5 in front of the oxygen because it's O2. That means I have 2 oxygens. So now I have 10 oxygens. Okay? Let's count all our points here. What did you multiply by 2? You didn't have to, because I didn't have an odd number and even number situation. In this case, huh? There's some others. You'll get a chance to do that. Okay? All right. All right. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Oh, we're going to have 26 points because we never count the middle set here. 26 points for that. The classification is combustion. So we're going to have 5 points for the combustion. That makes 31 points for this problem. Next problem. We have N2 and H2, and I don't have a physical state there. Well, you're supposed to know that if you have an elemental gas other than a noble gas, they're going to be diatomic. And so here's our diatomic gases. Nitrogen is naturally diatomic. Hydrogen is not naturally diatomic, and they're both gases. So these are both G. There's your physical state. Okay. If we're going to balance the equation, we need to list nitrogen and hydrogen. Need that grid to do the atom inventory. And I have 2 nitrogens, 2 hydrogens, 1 nitrogen, and 3 hydrogens. To get them balanced, I want to start by putting a coefficient 2 in front of the ammonia. And that'll change both these. So now I'm going to have 2 nitrogens and 2 times 3, or 6 hydrogens. So I need to put now a coefficient 3 in front of the H2. 3 times 2 is going to give me 6 hydrogens. Okay, and now that's balanced. So the classification of this is synthesis. We're putting together two smaller compounds to make a larger compound or a more complex compound. So let's count up the points you can earn for this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 points for that, plus the 5 for the synthesis. So that's 21 points. Okay. Here we have an element that's by itself, and there's an element in this compound that it's like. Okay, this is a metal, and that's a metal ion, so it's like that. We need to know, will this metal displace this metal? So we're going to look at the activity series, or in the case of this class, we're going to look at the reduction potentials chart. On the activity series, we need to know if nickel is higher than barium, but on the reduction potentials chart, we want to see if nickel is lower than barium. That's what we need for a driving force. Okay, so here's our reduction potentials chart, and let's see, we found nickel. There's nickel, and where is barium? There's barium. So where's nickel again? So barium is higher than nickel, or on the activity series, lower than nickel on the standard reduction potentials list. So will there be a reaction?
No.
No reaction. And that's worth 5 points. Alrighty then. We have ammonium chloride. Ammonium is a polyatomic ion. It would tend to stay together. And we have silver nitrate. Nitrate's a polyatomic ion. It tends to stay together. We have a two-part compound here, ammonium and chloride. Two-part compound here, silver and nitrate. If there's going to be a reaction at all, it's going to be double replacement. The front part of this goes with the back part here. The front part of this goes with the back part here. Front parts always remain front parts. And we have to predict what the product's going to be to find out if we have a driving force for a double replacement reaction. So let's put them together, NH4 plus the NO3. And then we're going to put the front part of this with the back of this, Ag and Cl. And we need to know what physical states these are going to be. Well, ammonium and nitrate compounds are always aqueous. So if you've memorized the solubility rules, you should know that this is going to be aqueous now. And there's no exception for ammonium or nitrate. And then chloride compounds are mostly soluble, but silver is one of the exceptions. Silver chloride is going to be a solid. Okay. We need to know we need to balance the formula. Well, silver is going to have a 1+ charge. Chlorine is going to have a 1 negative charge. Now, silver is in that area of the periodic table where you can have more than one oxidation number. Okay, we only use it for one of those. Okay, I haven't asked you to know that, but really for silver, that's kind of like we use that enough that you kind of should know that. Even if you didn't, however, as far as balancing the formulas, you can look at this formula and tell this is silver is a 1+. Okay, that's because nitrate, which you're required to memorize, has a 1 negative charge. And since you only have one of those in one of these silvers, the silver has to have a 1+ charge to have a neutral compound. Therefore, you're going to have a 1+ charge here. Chlorine has a 1 negative charge, and that's already balanced. Okay? Well, the formation of a solid here gives us a driving force. So this reaction does take place. It does move forward. So now we're ready to balance this equation. We know the reaction is going to occur. So we're going to write out all of our atoms. We have nitrogens, hydrogens, chlorines, silvers, and oxygens. Make a grid. Count everything. We have 1 nitrogen, 4 hydrogens, 1 chlorine, 1 silver, 3 oxygens. Over on the other side, 1 nitrogen. No, we got 2. I miscounted the nitrogens. I've got 2 nitrogens. 1 here and 1 here. 2 nitrogens. Over here, I've got 2 nitrogens. I have 4 hydrogens. I have 1 chlorine, 1 silver, 3 oxygens. That one's already balanced. Okay. And this is double replacement, we said. The classification is double replacement. Sometimes these types of reactions are classified as being precipitation reactions because this stuff precipitates. Okay, in an aqueous environment, this stuff is going to fall to the bottom. When the little powder form of this stuff settles to the bottom. All right, for the points, we need the ammonium here and the nitrate here and aqueous 1, 2, 3. Same here, 4, 5, 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 points plus 5, 26 points. Okay. All right, the last reaction. I have a more complex compound and on this side, and that's all I have, 1 compound. And over here I've got 2 of them. So this must be decomposition. I'm going to go ahead and classify this one first. Okay, and I'm just going to balance the equation. And I've got hydrogens and oxygens, pretty simple. And I'm starting out with 2 hydrogens on the left and 2 oxygens on the right. 2 hydrogens and 2 oxygens. Hey, how much easier can you get? That's actually not correct. I should have had H2O here, so I made it easy on you. Okay, there should have been an H2O. All right, so that's a typographical error on my part. Why? Because hydrogen peroxide breaks down into water. Okay, but since it's my error, I can't expect you to know that. If I make that mistake, I think I just originally had an O there or something. Somehow I laid it out. Who knows how that happens? But that's why hydrogen peroxide works. When you put it on cut sometimes, the increased oxygen actually is not a very favorable environment for bacteria. Plus, this reaction is catalyzed by the presence of certain organic materials like blood. And so what it'll do is it'll flake off the scab part of it and clean it out. That's what happens to it. It cleans out the cut or wound so that if there is anything trapped in there that could cause problems, it'll help to get it out of there. Okay, so it does 2 things. It gets rid of whatever's scabbing up already, on the surface anyway, and it is harmful to the bacteria. So it does 2 things as far as cleaning out a wound. Okay? All right then, let's see. 5 points for this. 1, 2, 3, 4, 5, 6. That's only 11 points. All right, let's see how much all that's going to be worth. I don't even have my calculator in front of me here. Anybody added that up yet? Say something? 146? Y'all trust her? 147? Is that correct? 146? All right, y'all want to vote on it? Somebody else add it up and see who's right. 146? Okay. There you go. All right. 146.